the next step in chapter 2, meaning boundary layer theory, is to complicate the drawing a little bit. In other words, there is a solid surface being swept by a fluid with a velocity, uniform velocity u infinity. Now we know there's a region called the boundary layer that develops. What used to be a uniform velocity profile becomes let's call it a deformed velocity profile here, one with a gradient at the wall. The gradient at the wall is responsible for the shear stress tau, which is equal to mu du dy at y equals 0. Okay? And of course, we have this skin friction coefficient formula, and the solution to the so-called momentum transfer problem is in hand. Game over. But what if there's a temperature difference between the wall and the fluid? So the fluid comes in with a temperature T infinity, and the wall is isothermal at T0, 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 and so on. Well, what happens is kind of the same thing, meaning that the fluid that's closer to the wall inherits a temperature similar to T0, while abandoning its original temperature T infinity. What is important to not to do is to assume that the heating effect from the wall, or cooling effect, depending on the relative temperatures T infinity versus T0, is to assume blindly that the transfer of heat into the flow proceeds to a thickness the same as delta. In general, that is not the case. There is a distinct boundary layer called thermal boundary layer with a thickness delta sub T, which in my drawing is smaller than delta, but could also be greater than delta. So the first step is not to assume too much. That is to say, well, there is let's call it the distance of vertical penetration called delta sub T. In general, not the same as delta. We know what delta is. Delta is x Reynolds number based on x to minus 1/2. How do we get delta sub T? Because delta sub T is the answer, or the key to the door that takes us to solving the problem. The problem is what I spelled out in the first lecture. The problem is to discover the relationship between heat transfer rate, in this case the heat flux Q double prime watts per meter squared coming from the wall, and the temperature difference. The temperature difference being delta T equals T0 minus T infinity. That is the problem. And the heat flux, you can see now why the fluid is important. If I plot the distribution of temperature in the fluid temperature is T infinity. It is T0 at the wall, and it is a distribution like this. The heat flux is of the order of k. Actually, it is equal to, because in the beginning I do not invoke scale analysis, equal to, and then the gradient of t with respect to y at the wall with minus in front because the temperature is decreasing, but my arrow is pointing upward. So the heat flux is the unknown. Via scale analysis, this unknown is the same as the conductivity of the fluid, delta T divided by delta sub T, because I am focusing my interests on this system, a system of length L and thickness delta sub T, different than the boundary layer discussed in the preceding lecture. So, nu is the system, which is delta sub T times L, or I wrote X here, but let's talk about L. And and nu is the unknown, which is the relationship between the heat flux and temperature difference. And the path to victory is to use the same technique plus one principle that we did not invoke already. So scale analysis, first the equations we use would be mass conservation in this region, du dx plus dv dy equals 0, and the equation that appears now for the first time is the energy equation, which is U in steady state, U dt dx plus V dt dy equals alpha d2t dx2 plus d2t dy2. That's what we don't put this in the bag yet. We'll put in the bag what drips down from this pair of truths. Scale analysis of this region. And clearly, from here, in this region, you have U infinity over L of the same order as V, I'll say V sub delta sub T, meaning the vertical velocity out of the boundary layer, meaning the fluid being pushed outward, that's V delta sub T, divided by delta sub T. From the second equation, after assuming slenderness, if you neglect slenderness, you get, obviously, neglect that. But on the left-hand side, you have a choice between U infinity delta T over L or V delta sub T times capital delta T over delta sub T. And on the right, you have only alpha capital delta T over delta sub T squared. Your unknown is the thermal boundary layer thickness. So delta sub T is called thermal boundary layer thickness. You simplify your life by dividing that way. Next, you make the observation that the left-hand side, two terms, is only one order of magnitude because this balloon appears here and here. So the left-hand side is of order U infinity over L. And then alpha over delta sub t squared. Easy, right? Meaning you have an equation for delta sub t, which happens to be wrong because I let slip into this a mistake that I did in the very beginning. This was before I wrote the book. And the mistake is the following. The scale of horizontal velocity in this region is not U infinity. Look at the comparison of boundary layer thicknesses in an exaggerated manner. This is the bottom wall. This is delta t, and this is delta. The horizontal velocity scale U infinity is at distance delta from the wall. In other words, I'm going to make simple drawings like in geometry, triangles. So U infinity is here. The other boundary layer, delta sub t, much thinner, is being rubbed by a flow that's slower. And the scale here, U sub delta sub t, is proportionally smaller than U infinity. So the mistake is to have written blindly U infinity here and here and here. What should have been written instead is U delta sub t, the same as small delta t over delta, and then times U infinity. This is what must be substituted in this location so that the punchline, and by the way, you have a formula for delta. That formula for delta is, once again, L Reynolds based on L to minus 1/2. After you make these substitutions, you obtain delta sub t, the thermal boundary layer thickness, is of the same order as Prandtl to minus 1/3, and then L Reynolds number based on L to minus 1/2. Clearly, this trailing factor is delta from one lecture ago. The Prandtl number is the ratio of nu over alpha. You get the idea here that the group started to be known Prandtl number because of boundary layer theory. Previously, there was no such ratio. And there's something else about the appearance of dimensionless factors. They're of two kinds. The dimensionless groups that persist are the groups named that way, not by the inventor of the group, but by the users of the group. And Prandtl was a very modest person. And so this is the main result, which beginning with the next lecture will be substituted into the heat flux equation in order to empower you to predict heat flux, or the relationship between heat flux and the temperature difference. Until then, check on me to make sure I'm okay.